Okay, looks like a lot of people are here now, so we'll allow people that are coming to continue coming, but let's get started. So today we're going to be talking about digital forensics, and Madison is going to be firing up a poll asking how many of you guys have heard of digital forensics before, if you have any experience of it with it, or if it's your first time hearing about digital forensics. So if you guys would please answer the poll when it's up, that would be awesome. But before we get started with forensics, there's an important announcement, just some important information. So next week's workshop is actually going to be a panel, and it's going to be about women in cyber. And for that panel, it's important that everybody, like all the students, are registered. So without registration, you will not be able to attend the panel. So let me just show you where you can access the registration. Just out of there. So you can access it on this link right here. I'm going to share that in the chat. So this is the link to the blog post about what the panel will be about. It's going to be talking about, women in cybersecurity, and there's going to be some females who work in cybersecurity who are going to be sharing their experiences. So it's really exciting. And if you scroll down to the blog, in the blog post, there's a register here button right here, link. So let me just share that in the chat. If for whatever reason you are not comfortable registering, that's okay. We will be sending a link post-workshop when the workshop is over. You can work something out with your teachers. You can maybe use your teacher's link or email if they're comfortable with that. So if you're not comfortable registering, there are other options. We will be sending a recording, but to attend that workshop, it's really important to register. And I've shared the link in the chat box below. So that's where you can register for it. So let's get back to forensics. So what are we going to be discussing today in Digital Forensics 101? We're going to be talking about what exactly is digital forensics. We're going to be talking about volatility. We're going to be talking about collecting evidence, numbering systems, which is how computers talk in the languages that they use to communicate. We're going to be talking about encoding versus encryption. And if you were here last week for the workshop on cryptography, then you probably now have a really good idea of what encryption is. So we're going to be talking about encoding versus encryption. We're going to be talking about file headers, hex editors, metadata, steganography, network traffic, and then Wireshark. And what's really exciting about digital forensics is that a lot of tools and techniques that are used actually by actual cybersecurity professionals. For example, Wireshark is a huge tool that is used so, predominantly in the cybersecurity industry. So getting that hands-on experience with Wireshark is going to be super beneficial for everybody taking part. I see a comment about I love Wireshark. Yeah, I do too. It's really awesome. And if you already have experience with it, then you're going to find some of the challenges for CTF, specifically in the forensics category, to be super fun and easy to do. And it's pretty simple to use it once you get the hang of it. So I think that's going to be the highlight of this workshop, is to actually use a tool that is so used in the field. So let's talk about what exactly is digital forensics. So if you want to give it a definition, it's collecting, examining, analyzing, and reporting digital electronic evidence. Now, why would we want to do that? So just like when a crime takes place and you have your forensics teams that comes, the same thing happens with digital forensics. If an incident occurs, if a data breach occurs, then you get your digital forensics teams to review all of that information, and their goal is to reconstruct what happened so that they can figure out exactly what happened, how the hacker got a foothold on the system. And when they did get a foothold on the system, how did they move through the network? And what did they corrupt? What files did they impact? What computers did they impact? Like, how huge of an impact did it have? So that's what digital forensics is all about. It's important to notice that a lot of times in digital forensics, there are cases that go to the court. For example, if an individual was found possessing illegal information or information that they shouldn't have. For example, the government finds that they've been, they have access to secret government level documents and they have to take them to court. Then the digital forensics teams would then take that person's computer or whatever, and then they would perform some forensics on it. So they would analyze the data that's on there, and then they would have to take all of that evidence to court. So a lot of times in digital forensics, it's really key because you have to take all of that evidence to court. And when you're taking that evidence to court, there are rules about how you collect that evidence, what you present to the court, what's admissible evidence. So it's a really, really key area of cybersecurity. But in Ctf Challenges, you're not so much asked to, collect evidence or examine or report it. It's more about analyzing that evidence. So, you're asked to analyze files, you're given file format and extensions, you're given memory dumps to see what exactly took place. You're given packet captures, which you can analyze using Wireshark. And then sometimes you come across what's known as Steganography, which we're going to be talking about in a bit, and that's super cool. So let's move on to the scientific process. This is the process by NIST. NIST is the National Institute of Standards and Technology. They're a huge governing body when it comes to cybersecurity. They, prepare a lot of guidelines for individuals and, organizations in cybersecurity. So their digital forensic scientific process looks like collection of evidence, examination, analysis, and then reporting. And each of the terms is pretty self-explanatory. Collection of evidence, you are collecting the evidence, you're examining that evidence and seeing what is actually evidence, what's not, then you're analyzing the evidence, and then finally you are reporting it. So this is a really key concept in digital forensics. You're not going to come across this in, nobody's going to ask a volatility question in a CTF, but it's really important to understand volatility and the role it plays in digital forensics. What it means is that more volatile data should be acquired first. And what is volatile data? It's data that is lost. For example, when a computer is shut down or unplugged, there is data that can be lost when you unplug the computer or when you shut it down. And that data is also called volatile data, and that's usually your RAM. So you have two types of memories. You have your random access memory and your read-only memory. And all of the process that's going on right now, for example, everything that's happening right now while I'm talking to you, it's being stored in the RAM. And so it's really important to see what is happening and in registers and memory, and that's stored in the RAM, and RAM is very, very volatile. And if I shut down this computer right now, then all of that information in the RAM would be lost. For example, if I shut down my computer, our connection would be lost and there would be no trace of it. That's why it's really important that if you do figure out that a certain computer has been breached or it might be impacted or affected, that you capture all of that information before shutting it down or before unplugging it, which is a really important concept. And usually they follow a specific order to collect data so that the critical forensics data isn't lost. And here is a list of from most volatile to least volatile. So we have your CPU cache, your registers, which are most volatile, then your data stored in RAM, files written to disk and hard drive is the least volatile. Things that are in your hard drive usually stay in your hard drive. You save the file in your hard drive, it usually stays. After you shut down the computer, it does not disappear. So that's a really key concept important concept to understand in forensics, in digital forensics. Now, collecting evidence, when you're collecting evidence, you can start capturing the RAM, which is really key. You capture system images, and it's really important to get a bit-by-bit image of the drive. And I'll explain why. It's because drives have what's known as slack space and free space. And in that slack space and free space, there's often remnants of deleted files and deleted data. So when you do a bit-by-bit image, it captures all of that residual space and slack space. So there's important artifacts in those sections, so it's really important to do a bit-by-bit image of the drive. Then you have your network traffic and logs to see who was talking to your computer, who was speaking in the network, what was really going on. Then you can take screenshots as well. A lot of times if you come across if you're going through, let's say you're going through a cross-site scripting attack, as we discussed in web security, and you get a pop-up on your screen, it would be really important that you take a screenshot of when that happens so that you have evidence of it, because it would be really hard to prove that it happened without some sort of, a screenshot or some sort of screen recording evidence of it. Then we also talked about hashes in the cryptography workshop, and if anybody remembers, can anyone remind us why are hashes so important? Does anybody remember? Yeah, to make sure the data is legit. Yeah, exactly. So for integrity purposes. So when you're collecting evidence, when you capture that bit-by-bit image of the drive, before you capture it, it's really important that you hash it, and then afterwards, exactly, hashing is one way. And then after you capture the bit-by-bit image, you also create a hash for that. And what's going to happen is that's the only way in court you'll be able to prove that it was not tampered with, and that if the hash is matched, then you know that it is admissible evidence. And in the courtroom, they're very strict about this type of data because, computer data is so sensitive. You can manipulate it, change it. It's really easy to manipulate and change. So it's hashing is a thing that proves kind of that the integrity is still there, that the data hasn't been changed. So that's the importance of hashing. Just another reminder, if you're sending a message in the chat, it would be nice if you could share the message to everyone and not just to all panelists, so that everybody could participate in the conversation and everybody can see the messages. So yeah, that's collecting evidence. But now, these are some of the main sources of what we collect evidence from. Does anybody know what other sources would be important to examine during a digital forensics investigation? What are some other things that we should look at? So let's talk about what other sources we should examine for digital forensics for collecting evidence. So any type of history, correct. We should look at everything that was happening. Browser history is important. So let's take a look at other stuff that, it's important to collect. So we have our storage, we have our desktop, laptop, hard drives, external hard drives, USB hard drives, our hardware and OS, networks, what's happening in applications, to look at application data, to look at logs, which is really important, network, your intrusion detection system and intrusion prevention system logs, and your firewalls, your memory images, your RAM, your CPU cache, metadata, which is hidden data in a file. It's not hidden, it's there, but it gives you more information about a file. And we're going to be talking about metadata in just a couple of minutes here. And also deleted files, which can be found through, getting a bit-by-bit image of a hard drive and looking at the slack space and looking at the free space on the drive. And there's multiple other sources to examine, call histories, text messages now with mobile forensics being such a big area, memory dumps. There's so much, like someone mentioned history, browser history. There's just an abundance of sources that need to be examined. And it also depends on what type of an attack took place or what type of an incident took place. If you're just doing an annual report type thing. So it's really important to know that and then to examine all the sources that need to be examined. Now, before we can really analyze any of that information, before we can analyze a memory dump or we can analyze a binary file, a computer file or a computer program, it's really important to understand numbering systems. And why is it important to understand numbering system is because the computer doesn't take instructions. In, plain text. We can't tell our computer, open this file for me. It doesn't take information like that. Everything that you do, it has a binary attributed to it. It understands binary. So binary is the language that computers use, which many of you might have heard of if you're taking computer science or computer engineering course, is it's either a 1 or a 0. It's either on or it's off. And that's how computers communicate. So A single 1 or 0 is the smallest unit of data, and it's called a bit. So binary, when we talk about bits and bytes, we're referring to binary. And binary is usually in base 2. So to make it more understandable, binary is often converted into hexadecimal, and it saves up a lot of space as well. It just makes things simpler. So it's really important to understand hexadecimal as well. Hexadecimal is base 16. There are 16 total values represented by a single digit, and they go from 0 to F. Starting from 10, 10 in hexadecimal is represented by A, 11 in hexadecimal is represented by B, 12 in hexadecimal is represented by C, and so on until, and 15 is represented by F. That gives us 16 digits from 0 to F. Each hexadecimal digit represents 4 bits. So if you had the 0 on its own, it would represent 4 binary bits. And so 1 byte is equal to 8 bits, and that is a unit of data. 1 byte is equal to 8 bits. So if each hexadecimal digit represents 4 bits, then you could represent 8 bits of binary using 2 hexadecimal digits. So whereas if you were representing it in binary, you would have 8 bits of data, but now that you have it in hexadecimal, once converted, you're only representing those 8 bits using 2 digits, which makes it more compact. That's important to understand for why things are converted to hexadecimal. Then we have ASCII. ASCII is an encoding scheme. So computer reads the data as binary, and it's to represent letters and symbols. It must be converted to ASCII. Without ASCII, because the binary is just numbers, right? So to actually, for the computer to actually understand characters like your A, B, C, D symbols, it needs to be encoded into ASCII. So now let's take a look at all of these things, each of these numbering systems in more details, and really understand how they work and how we can convert between all of them. So let's look at binary over here. So as mentioned, 1 byte is equal to 8 bits, and each of this is a bit. So there's 1 bit, 2 bit, 3 bit, 4 bit, 5 bit, 6 bit, 7 bit, 8 bit. 8 bits is equal to 1 byte. And binary is base 2. So over here you would have 2 raised to the power of 0, 2 raised to the power of 1, 2 raised to the power of 2, 2 raised to the power of 3, 2 raised to the power of 4, and so on and so forth. And it doesn't end here. You can keep on expanding it. You can keep on having 2 raised to the power of 8, 2 raised to the power of 9, and so on and so forth. So this value over here to the rightmost, it's the least, known as the least significant bit, because it doesn't have much value. It's 2 raised to the power of 0, right? So it's the least significant bit. But the highest value, which is leftmost, is known as the most significant bit. And understanding that is going to become important when we look into steganography. But it's just important to know that the rightmost bit is your least significant bit, and your leftmost bit is your most significant bit. So let's talk about converting binary to decimal and, doing the opposite as well. So let's look at this. So let's convert, we have this binary number, it's 10110110. How exactly would we convert that to a decimal? Converting that to a decimal is very, very simple. So all you're going to do is you're going to have this chart of your 2's raised to the different powers and just slot all of these values in. Again, 1 is on, 0 is off. So over here, we have 1 in the value of 2 to the 7. So that means we have 128 plus 0. We have 1 bit over here, which is 32, which is 2 to the power of 5. So it's 32. We have plus 32. Plus we have another bit here at 2 to the power of 4, which is 16. We have plus 16, plus 0, plus 4, which is 2 to the power of 2, which is 4. We have a bit over here, which is 2 to the power of 1, aka 2, and then plus 0. And would somebody mind doing the math for me and letting me know what, when you add all those values, what it comes out to? Yep, it comes out to 182, correct. So now let's actually, it's important to understand that we're doing this because it's important to understand the background and to understand how it really works. But in an actual CTF challenge, I highly recommend you don't sit there and do the conversion yourself if you want to. It's going to be time consuming. You might get a crazy number too. So let me show you an easy way of doing that. And we're going to go binary to decimal. So let's just check and see if this is actually working. So our binary number was 1011, 1011, 0110, 0110, 0110, oops, 0110. And if we convert that, we should get 182. We get 182. Perfect. That's wonderful. So now what about if you had to do the reverse? If you had to convert 182 back into binary. So we would do the reverse. First of all, we would start off with the most significant bit, or we would move down and see where does 182 go in fully. So after 128, we would have 2 to the power of 8, which I believe is 256, and that doesn't go into that, so we don't have to look. We have to start looking towards our right. So we have 2 to the power of 7, so we have 128. So we would check. I'm going to use my phone as a calculator. So what we would do is okay, so does 182 go into 128? Yes, it does. How many times does it go in? It goes in once. And if it's going in more than once, it's binary, you have to go more to the left. It should only go in, there should only be ones and zeros. So 182 does go into 128 once, so we have 1. Now let's subtract 128 from 182, we're left with 54. So after 54, what does 54 can go into? Well, what can go into 54? So we can have 32 go into 54 once. 64 cannot go into 54. It's too large. So 32 can go into 54. So that's 1 times 32. So we would subtract then 32, and we are left with 22. Can 16 go into 22? Yes, 16 can go into 22. So we would subtract 16. And now we have 6. So obviously 8 cannot go into 6, but 4 can go into 6 once. So now we would subtract 4. We're left with 2. And 2 obviously can go into 2 once. And that's how you would do the reverse when you're converting back from decimal to binary. So I hope that's kind of clear, but also in CTF, it's recommended and more simpler to just use an online calculator or converter to do the conversion for you if you have any problems like that. And in Pico CTF last year, I'm sure there were some problems of conversion in the general skills category. So they're pretty simple. Just plug it into your calculator and the conversion will be done through the program for you. So that's binary. Now let's talk about hexadecimal, which is base 16. So we're going to convert, hexadecimal is base 16. So like base 2, we're starting with 16 to the power of 0, 16 to the power of 1, and so on and so forth. And again, this is the least significant bit, and this is the most significant bit. So we're going to convert 182 into hexadecimal. So how would we approach that? Well, let's see. So we have our table over here, and we have 182. And no, there will never be a situation where a number it can go into the decimal twice, But if it's going into the decimal twice, you have to keep moving. You have to keep moving to your left. You have to make sure it only goes once, because binary is only ones and zeros. So it is possible that it can go into a decimal multiple times, but you have to keep going to your far left because it should only go in once because of binary. Binary is only 1 and 0. Exactly what Noah said, it would just fit into the next largest one. So you keep moving forward. Okay, so back into Hex, unless there are more binary questions which we can address before moving on to hexadecimal. Okay, I don't see anything. So let's now convert 182 into hexadecimal. So here we have our hex chart 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A. So 10 is represented by A, 11 is represented by B, 12 is represented by C, and 13 is represented by D. 14 is represented by E, and 15 is represented by F. So knowing that, and knowing that hex is base 16, does anybody want to take a shot at figuring out how we would exactly convert 182 into hex? The answer is right here, but I just want to see if anyone wants to take a shot at the process of how we would go about converting a decimal into a hexadecimal. Powers of 16 exactly, and then checking how much the number fits into each respective one. If the base 16, we would times the number, let's say 5 by 16 for part of it. Yeah, exactly. So the process of converting a decimal into a decimal into hex is literally the same. So over here, we have our 16 to the power of 0, 16 to the power of 1, 16 to the power of 2. Each digit in the hexadecimal represents a power of 16. So just multiply each hexadecimal digit, its corresponding 1 by 16, by its power of 16. Exactly. So let's pull up A. So it doesn't go into Z. Hex only goes from 0 to F. So Abira is gonna help with that. There is no Z. Hexadecimal, let's clarify, is only from 0 to F. That's it. And then it would keep repeating. Okay, so let's look at a hexadecimal table, because I think the one I have up is not very, it's kind of confusing. I don't know why I just went from Google to Google. Let's look at the images. I want a horizontal. Let's see if I can find a table for you guys to look at. Let's see if this is a good table. Okay, let's just go back and let's just do it manually. So what is 16 to the power of 0 is 0. What is 16 to the power of 1? What is 16 to the power of, what happens if the number is bigger than 16 to the power of 16? I've never had to do a problem where the number is bigger than that. Okay, let me just get an online calculator because I don't have one and I want to calculate the 16. 16 to the power of 2 is 256. Yeah, 16 to the power of 1 is 16. 15 to the power of 2 is 256. So then we're going to see how many times it fits into each. So we have B6, and B6 is 1 byte of data. It's 8 bits. What we're going to do is we're going to take 6 because it's going to be the rightmost, and we're going to raise it to the power of 0. So 6 times 16 to the power of 0 is equal to 6. B, which is after that, is going to be 11 times 16 to the power of 1, which is equal to 176. And why is B going to be 11? Does anybody know? Why did I let B be 11? Why did I not leave it as B? Because the hexadecimal value for 11 is B, which is why I converted it into decimal form. So when you have the letters, you have to make sure you convert them back. Yes, because B in hex represents 11. Exactly. You're all correct. So that is why it would be 11 times 16 to the power of 1, because that's 16 to the power of 0, 16 to the power of 1, and 176. And then 176 plus 6 is equal to 182, right? So now let's do the reverse. I'm going to get my calculator. So we have 182. So now we're converting it into hex. What we're going to do is we're going to do 182 divided by 16. So we're going to get 11. It goes into 16 11 times. So we have our first letter, B. That becomes B. Now we're going to times that. We're going to do 16 times 11 is 176. So we're going to subtract 182 minus 176, and we're left with 6. Because 6 in decimal is also 6 in hexadecimal, we get B6. So that's the conversion from decimal into hex and from hex into decimal. I know that's a little bit confusing, so if there's any questions, we can solve those questions before moving forward. Yeah, B6 is equivalent. So 182 into hex is B6. Okay, I don't understand the first part of the answering process. Okay. Yeah, let's repeat the last part. Let's go over it again. So let's say you're converting 182 into hexadecimal. So you have base 16, but you want to see how many times does 182 fit into 16, right? So we would do 182 divided by 16, which is 11.375. So you know that at least 182 can be divided by 16 11 times. So that's our first value. We have 11 is a decimal value, but we have to convert it to hex. And when converting it to hex, the equivalent of that is B. So we would have B. So that's that much. But it goes into, it doesn't perfectly go into, 182 cannot be perfectly divided by 16. There's a decimal space, so we're going to have some remnant. So what we're going to do is we're not going to multiply because we have one whole 11 spot taken. So we're going to see how much that is and how much is left over to convert the rest of it. So 182 minus 11 times 16, which is 176, and we get 6. And when we're converting 6 from decimal form into hexadecimal, 6 is just equal to 6. So therefore, 182 becomes B6. Does that make more sense, or is that still a little confusing? So it's still kind of confusing. So maybe Abira can help you out. If you're having trouble understanding it still, then please, you can message Abira or all panelists, and then Abira can help you out. So let's move on from hexadecimal to ASCII. So hexadecimal is base 16. When you're converting into hex, you make sure you divide that value by 16 because it's a base 16, and then you see where it fits. And then the opposite when you're converting back from B6 into decimal. Let's talk about ASCII. So ASCII is a code for representing 128 English characters as numbers, with each letter assigned from 0 to 127. And most computers use ASCII codes to represent text. So as you know, computers cannot, they only speak in numbers, they speak in zeros and ones, so they need some sort of format to be able to translate that text. So when we're typing in paragraphs and sentences, they need some sort of format to understand what we're saying. So this ASCII allows computers to transfer data easily because it allows you to, contain those characters. For example, right, let's look at this. This is an Ascii chart. And so, this binary represents a null character. If you want to represent, let's say, if you want to represent the character A, it's represented by a hexadecimal value of 41. If you want to represent the actual number 0, it's represented by ASCII hexadecimal value of 30, and that's all ASCII does. It has a code for representing different characters. Like, how can we represent a space bar? If you're typing and you want to do a space, how can your computer understand that? And that's a hexadecimal value of 20. And so ASCII is an encoding scheme. So let's talk about encoding versus encryption. So as you remember from last week's cryptography class, encryption is when you transform data from one form to another, but an encryption algorithm is used alongside a key. So there has to be a key there. If the key is unknown, the message cannot be reversed. With encryption, you're trying to, hide the data. You're trying to conceal the data, but with encoding, there is no key. You're not trying to hide the data. All you're trying to do is make it easier to transmit data or efficient storage of data. So it's just transforming one data to another form. So, for example, converting hexadecimal to ASCII is a form of encoding. And you can easily convert back from ASCII to hexadecimal or hexadecimal to ASCII. There's no key. You're not trying to hide any messages. You're just encoding the message so you can transmit it across computers more easily for efficient storage of data. That's the main difference between encoding versus encryption. So now that we understand a little bit about hexadecimal and binary and how the computer, uses that to represent data, let's talk about file headers and file signatures. So usually we know what a file is because we have an extension at the end of the file. For example, if you have hello.pdf, that's a PDF file. Hello.docs, it's a document file. If you have hello.png, PNG, it's an image file, or hello.jpg, that it's a JPEG file. So that's for the extension, but what files also have are what's known as a file signature or a magic byte. It tells you what type of a file is, and usually they're around 2 to 4 bytes long, and each byte is, as 8 bits, so you can calculate how many bits that would take up in a binary file. So you can view this extension or this, these magic bytes using a hex editor or a hex viewer, because most of these files are represented using hexadecimal. Oops, I forgot to remove a note that was for myself, which was to explain what a hex editor viewer is, and we will be discussing that in the next slide. But anyways, so you can use that using a hex viewer and a hex editor, and all a hex viewer editor is, it allows you to view binary files, it allows you to view them, it allows you to analyze them and edit them. So for example, PDFs has a file header of 25, 50, 44, 46, 2D. And obviously when I open a PDF file, I'm not going to be able to see that. But if I view it in a hex editor or hex viewer, I will be able to see that. And also there is what's known as a file command, which will tell you the header which will tell you the file header has been interpreted, allowing you to figure out what type of file it is. So let's look at both ways we can figure it out. So let's open up a PDF file using a hex editor. So my favorite hex editor is Hex Edit. Let's see what the link is. It's this one right here, hex.it. It's an online hex viewer hex editor. So I'm going to open up that PDF file. Let's see what PDF file I have. Let's open up our cryptography slides from last week. Let's see. So it says PDF right here, but how is it represented in hexadecimal? Let's go back. So a signature for a PDF file is 25, 50, 44, 46, 2D. Do we have that? Yes, we do. We have 25, 50, 44, 46, 2D. So we have a byte here, a byte here. So there's 4 bytes right here. And so that allows us to know that it's a PDF file. For example, if I was to remove the PDF extension, I wouldn't know what type of file it is, and I could view it using the file header. So now let's do a challenge using Untitled Ctf that will allow us to see how these challenges can look like in a CTF environment. Go to picoctf.org and log in. Should make that a little bit bigger. You guys can see. And we're going to be doing a forensics challenge called extensions. So when you see like anything with extensions, you know, like it might be about file header, file signature, or magic bytes of a file. So the clue is, this is a really weird text file. Can you find the flag? How do operating systems know what kind of file it is? And make sure, okay, we don't need that part. So let's download this text file. Let's just save this file. And let's now open up terminal, a command line, and let's refresh some of our skills. So does anybody know how I can get into my downloads folder? Because I'm pretty sure that's where my file has saved. Perfect. I'm really glad to see that you guys remember how to get there. So let's cd into downloads and let's see what's here. And my flag.txt file is here. So now it says it has a weird extension and it shouldn't be opening. So does anyone know what command I can use to perfect. You guys are a step ahead of me. File flag.txt. Let's see. This command is going to give us what the file format should be. Okay, so it's telling us that it's a PNG image. So our next step would be to change this file flag.txt into, flag.txt into flag.png so that we can view the file. So let's see if it's, okay, now it's PNG. I'm going to be using Ristretto, which is a PNG or image viewer, and it comes by default on Kali Linux. So you might have another one installed, so you can use whatever other program you have to open up the PNG file. You can use the GUI as well. You don't have to use the command line. So I'm going to try opening that up. And there we go. There is our flag. As you saw, that knowing the extension helps, because without the extension, we wouldn't be able to open up the file. So that's one way to do it. Let's go back here and let's go into extensions. Again, let's go into this challenge and let's see if we download it, what happens. If I download it and I open it, this is what I get. I mean, I'm lucky that it's telling me it's a PNG file right here. So, but I can also, where can you find an image viewer? So if you do install a Linux distribution, a lot of them come with the default one. Just look and see which one your distribution comes with. Kali Linux comes with Ristretto by default. So I don't know if you're using another distribution, you might have a different image viewer. And you can also install, if you have a preference, you can also install a new one. Another way to view that file would be to open a file right here. We have flag.txt. And now, here's a really useful resource, which is called Gary Kessler's File Signatures Table. So let's just look for PNG. Here we have PNG. So it's telling us that a PNG header looks like this: 8950 4E 47 0D 0A 1A 0A. So let's see. If we were to look at that file and we were to recognize that it has that header, then we know it's a PNG file. So that's another way to do it. So there's different ways of solving these problems, and I'm just sharing two of them, and there's multiple other ways that you could solve this problem as well. So it's really important to understand file extensions and file headers, because sometimes you might be given a corrupt file where the header is messed up, which is why the file isn't opening. And if you guys want to practice one that will really, it'll challenge you a little bit, but it's not challenging at all, you will need to download a Hex editor for it. It's the corrupt challenge in the forensics category on Pico Ctf. If you want to practice looking at a corrupt file, do the corrupt challenge. So now that's a little bit about file headers. So we looked at how we can use an online Hex editor to view the header of the file, and we can also use the file command, which will tell us what the format of the file is. Let's talk about Hex editors. A Hex editor or a binary file editor is a computer program that allows for manipulation of the fundamental binary data that constitutes a computer file, aka, or meaning that it allows us to edit and view binary files, which are usually written in hexadecimal or ASCII or binary. So why is this Hex editor useful? Because you can examine and fix corrupt files using it. You can use it for reverse engineering to understand what a program is trying to do. So here are some free Hex editors that for different operating systems. So we have HexHXD for Windows. You could download that if you're going to be using Windows as your main OS. You can use HTTPS Hex.it, the one that I was using just now. That's the link for it. You can use, and that's a free online tool, so you don't have to download anything. The only thing I would recommend downloading one is that you can edit and manipulate it easier than you can on an online tool. And then we have HexFind, which is on Mac, which is the one, if I'm using my Mac, I like to use. And then we have Bless, which is a Linux one, and honestly, Bless is a really amazing Hex editor. It has a lot of advanced features, and it's very useful when doing reverse engineering, which we'll be talking about in the next workshop. So let's look at how we can use a Hex editor exactly to analyze a binary file. So the challenge we're going to be looking at is from Pico Ctf, and feel free to follow along. We're going to be looking at the White Pages challenge. So let's download this file, and we didn't get any hints for this one. So let's say when you open this, you are getting this. This is all. So does anyone have any suggestions of what we can do to try and solve? Like, pretend this is the actual challenge, and you're given this type of a file. There's nothing in it. It's blank. There seems to be some sort of data though, because I can highlight it, but I can't see it. What should I do at this point? Does anyone know like how I can proceed with this problem? Yeah, we could find the file type. We could plug it into a Hex editor. Let's plug it into a Hex editor to find what the file. Yeah, let's see. Like a lot of you are recommending it to put it into a Hex editor. So let's put it into a Hex editor. And that is a whitepages.txt. Okay, so this is what I am getting. This is the file. This E28083 does not look like a signature I recognize, but anyways, let's check. Let's check Gary Kessler's list of signatures. Let's do E280. Okay. Yeah, so this is not a recognizable signature file header. So what can I do as my next step? Do I notice any patterns? Well, one thing I do notice is that there's only two types of really data in here. There is RCA, which I feel like it's represented by E28083. And then we have a space right here, which is represented by 20. Let's see if all the spaces are represented by 20. Yeah, all of the spaces are represented by 20. Okay. Yeah, so the fact that there's only two types of representations, it leads me to believe that this could be a binary file. So let's try opening it up in my Hex Editor, which I hope is, there we go, it's right here. So this is the one that you can use on Mac for free. Let me open this file in this editor. Okay, let's go, and we have our whitepages.txt. Let's open that up. Okay, so let me not make the view so confusing. Let me make it big like this. Okay, so now I have it. Does anyone know what my next step should be? I've opened it up in a Hex Editor, and I know it's a binary file, so now what can I do? I mean, I know it's a binary file, but it's not allowing me to view it as a binary. I'm just viewing it as a hexadecimal right here, and as what I presume to be ASCII right here. Remove the header. Yeah, so what everyone is suggesting to me, what most of you are suggesting, is that to see if I can convert this into binary. So let's try to convert this into binary manually. So keep in mind that if there's a text message, we need to use ASCII to obtain that text message because it allows us to view characters. And right here we have ASCII. So let's convert. So usually in all of your Hex editors, there's going to be a find option, and most of them work the same way. You can use the find option to replace things. So before we saw that there was two types of characters. There was this E28083, which was representing this AE, or now it's comma AE because my computers may be using a different encoding scheme. So let's replace that 8083. So what should I replace all of those E28083s with if it's a binary file? Maybe I could replace it with 0, right? But if I replace it with 0, I'm going to lose that ASCII encoding and I won't be able to extract the message. So how about we convert it into ASCII but like a binary file? So what is the ASCII representation of 0? Does anybody know what the ASCII representation of 0 is? So I'll give you the answer. So the ASCII representation of 0 is 30. So we're going to replace all of these E28083 by 30. So let's replace them all. So now we have, as you see on the right, because this is converting it from ASCII, we have a bunch of zeros. So now we have all these zeros. So now what we're left with is these empty spaces right here, which I presume are being used up by these 20s that we have, because now the rest of it's 30s and 20s. So let's replace 20. Oops, I did not mean to do that. Let's replace 20 right here with the ASCII representation for 1. which is, so somebody is asking if I can show this for Hex.it for students who don't have the software. So as I mentioned earlier, to edit and manipulate the binary files, you're going to have to download a software, a Hex Editor, because let's look at it in Hexed. We cannot, so I'm going to enable replace. So I'm going to search for, let's say, 20, and replace 20 with 1, right? And then, but the thing is, I'll have to do this one by one. And to replace each and everything one by one, it's going to take maybe it's going to take a long time. So which is why I recommend, and I gave those free Hex Editor recommendations, because during a CTF, you're going to have to have a Hex Editor downloaded to do many of the challenges, to do reverse engineering, to do these type of challenges. So it's really important that, and they're all free softwares. All of the ones I recommended are free, 100% safe. So I would really recommend everybody to download a Hex Editor. Correct. 31 is the representation of 1. So we're going to replace all of the, yes, let me repost all of the Hex Editors in the chat before we move forward in case you guys want to. Here we go. So these are all of the Hex Editors. And there's many more. These are just like a very few of them. There's so many more Hex Editors that you could use. And there's a lot of free ones. You don't have to pay for it. You can download it, and they're pretty simple to use. So as we were doing this Hex editing this file, we replaced all of the E28083 with 30 because that's ASCII representation of 0. And now we're going to replace all the 20s, which are left, with 31, as somebody suggested. We're going to replace that with 31 because that's the ASCII representation of 1, and we're going to replace all. So now we have this is an ASCII, this is 30, 30, 30, 30, 31, 30, and it's a binary file. And now we have the binary file, the binary representation right here to our right. So now we have this. Does anybody know now what can be done with this binary data? What could I do with this binary information to get the flag? Yeah, we could put it into a converter for binary. So let's convert it. Let's go back and find a binary to, and to see a message, we're going to have to convert it into ASCII. Let's convert this binary file to ASCII. Let's find a good. Okay, this is a good one. Let's put all the, so we have all of this, and now let's translate it. It would have been possible to convert from hex to binary, but in doing so, you wouldn't be able to capture the characters or capture the message, because to really read that information, you would need ASCII there, if that makes sense. So now let's translate it and see what happens. And there we go. There is our flag right over here. I know this was a bit of a challenging, I would say this is definitely one of the more challenging problems, but I would say that it's really key to understand how the numbering systems work, how binary, hex, and ASCII work, and to download a hex editor and play around with some hex files and play around with some of these challenges on your own on the Pico CTF platform, so you really understand. And let me see if I can explain that one more time. Let's close this file and let's open it again. So let's walk through this process again. We opened it up in Hex Editor for many reasons, because we knew this is a forensics problem. So we might have to, change, we might have to view the, as you guys recommended, the file header to see if it's a different type of file. And we did, and we didn't see any particular file header. But what we did see was there were constantly repeating two characters, which were E28083 and 20. So the space right here was represented by 20, and these characters right here were represented by E28083, and they kept repeating. And because there were only two types of representations, it led us to believe that this could be a binary file. But this binary file was corrupt because right here we have hexadecimal, and we don't have we can't see any of the data because we need to convert it to ASCII. So we converted it to the ASCII representation of binary, which is 30 and 31, because 30 in ASCII 0 is 30, and in ASCII 1 is 31. When we converted all of that, it allowed us to see what the ASCII file actually looked like, and that it gave us a neat representation of 0 and 1, so we could see that that ASCII was being represented, and we could see the binary on the right-hand side. And then we were able to convert that binary back into ASCII to see exactly what the message was. So that's the process that we follow to solve this problem. So let's go back, and so it's really important that you play around with a hex editor. And somebody asked if it would matter if we converted first E28083 or 20, and it does matter because I think the message will get changed. But let's just try it out. So let's see what happens if we change it. So let's replace E28083 with 31, which is the ASCII representation of 1. Replace all. Replace all. Why isn't, oh, my bad. E28083 to 31, replace all. And now let's replace all the 20s to 30s and let's see what happens. Okay, so we see our binary is a little bit different from what it was before. It would be really cool if it did output the same message. Let's go back to our binary. So as you can see in this one, it started with a bunch of zeros, and in this one, it starts off with a bunch of ones. And we pasted it, we translated it, and we would get this message in ASCII. So you could, during the challenge, if you wanted, like if you're unsure, that's the thing. It's all trial and errors with some of these problems. So maybe someone would have approached it doing 31 and then 30, doing ones and zeros, but then they would have seen that it didn't make sense, and then they could have tried the other way. So it's really important that if one solution doesn't work, that you don't give up, and that if you feel like you're going in the right direction, you keep moving forward. You just change your approach a little bit. So that, so that you could have done it that way, but then you would have seen that it doesn't make up anything that makes sense. So then you would do the reverse, and then you would eventually get the flag. So it's really important to not give up when doing these problems. And the only reason I knew to do that first was because I did this problem prior, so that's why. But I did do a lot of trial and error with this problem as well. So it's definitely one of the trickier challenges, but your knowledge, you can slowly, walk through the problem and slowly see how we did in the class, how we slowly understood that it's two representations. It must mean binary, so then we converted it and so on and so forth. So let's talk about metadata. Metadata is hidden data, which provides information about the context of a file's data. When you look at a file, you're not going to see the metadata right away. You have to use a metadata tool or look into the details of the file to see that metadata. It's not obvious at a first glance. Images have what's known as Exif, exchangeable image file format data, embedded in them. And what this data does is it has a lot of important information about the images. For example, it talks about maybe the camera that was used, the program that was used to create that software, maybe it was Photoshop or Illustrator. And a lot of times Exif data can also include exact GPS coordinates and images. So a lot of times now, most of the social media websites, when you upload an image, if you have your location enabled, and with each image, those GPS coordinates are also being saved. So just a safety tip to make sure that in your picture settings, you disable that option. So now when you upload pictures to social media, most of them strip that metadata before it goes online so that no one can download it and, try to figure out what that metadata or what the GPS coordinates are. But it has a lot of hidden information. During forensics, metadata can be really helpful to analyze a file. There are tools that you can use to strip the metadata completely, and then a lot of times people use those tools to strip the metadata so that no further information can be extracted from the file. But a lot of times people forget, and metadata can give away a lot of information. For example, who created the file, when it was last modified, last opened, and etc. So we're going to do another Pico Ctf challenge to view the metadata, and we're going to use a tool called Exif Tool. Exif Tool it depends on the distribution you have, but it is included in the libraries, in the Linux libraries. So installing the Exif Tool is really easy. It's 2 command lines. You have to sudo get update install to make sure all your libraries are updated, and then you would install it from the library. It's 2 commands. It's very simple. You could check to see if you have it in your distribution, but I would definitely recommend downloading this tool. It's just a command line tool to make sure that you can strip the metadata. And I'm pretty sure there are online tools too. There are online tools that you can use to view the metadata of a file by uploading it, but this one, Exif Tool, is really good. So let's do a demo. So let's go into Pico Ctf, and let's look at, well, this challenge says so meta. And a lot of times I found in Pico Ctf, the titles give away a lot of hints. So that's really helpful. So in the hints for this file, it says, let me just move this over. It says, what does meta mean in the context of files? And ever heard of metadata? So it gives away a lot of hints actually. So let's look at this picture, and let's save this file. And let's go back to my terminal right here. Let's see if it shows up. Yep, so it's there. So the command for Exif Tool is just Exif Tool, and then you put the file that you want to look at, which is image.png. And this is going to give us all of the metadata of the file. So as we can see, we have here the file name, the file permissions, the file type extension, the tool that was used to create it, which was Photoshop, and the artist. And interestingly enough, the flag is right here in the artist section. But as you could see, this is a lot of the metadata that came with this particular image, and the Exif Tool will allow you to view that metadata. There are also online tools that you can use to look at that. If you go online and just look up metadata viewer, and you can plug in the file and view the metadata online as well. Yeah, if there's a lot of metadata, you could use grep. Let's see. So let's grep for Pico. And there we go. That was a really smart suggestion. And if there's a lot of metadata, you could for sure use grep like that. So that was one of the more simpler challenges, and they gave away a lot of hints. So it's really important to remember. And a lot of times in challenges, they will just give you a file. They're not going to tell you what to do, but that's what forensic specialists do. They have files and they really don't know what to do with it, so they try different things. You can look at the file header. You can open the file using a hex editor. You can look at the metadata of the file, and you can really just look at all the details of the file, and that's going to give you some hints and clues about what to do. Does this file work on the Pico provided shell? Yeah, so during the competition, any of the tools in the shell you have, a lot of the tools are pre-installed, and you can use them. And I'm pretty sure that if they had that metadata problem, that Exif Tool would have been installed as well. And you know what? I will test it out on the 2019 Pico shell, and I will send an email to your teachers and supervisors to see if some of these tools are available in the shell. But for a lot of them, you can't, you have to go outside of the shell. You have to use your own operating system, for example, to view and edit hex files and so on and so forth. Okay, so that's a little bit about metadata. Let's talk about steganography. So steganography is the practice of concealing data within other data. And steganos means covered and concealed in Greek, and graphin means writing in Greek, and that's what steganography comes from. It comes from the fact covered writing. Now, in encryption, we are trying to hide a message, but it's known to people that we're trying to hide the data. In steganography, you're trying to hide the fact that you're hiding something. So it's not supposed to be really obvious that you're hiding something, right? So an example would be taking a file and hiding another message inside of it. So now I have a little challenge for you guys to do. I'm going to stop sharing my screen, and I'm going to share a file with you. And I want to see if you guys could see what the hidden message in this steganography image is. So here is the image. And I'm going to give you guys a second to see if you can figure out what the hidden message is in this image. This is a very simple example of steganography. A hint that I could give you guys is that you don't need any tools or anything to solve this challenge. Yeah, so this is a very contrived example of steganography. And obviously in real life, a hacker would not use this method to conceal data. There's other ways that they would do, or if anyone's trying to send a secret message, they would definitely not use this way because it's almost very obvious in a way. But this way is used, and it has been used. If I matched the colors more, it would have been harder to see, and it would have been harder to see, right? So this way, it has appeared in Ctf Challenges before. So sometimes, like, I myself have been stumped by some of these challenges because I'll be forever, like, trying to figure out what's happening, but then the answer is right there in front of our eyes. So the password is here. You have to zoom in. If you save the file, onto your computer and then you zoom in, it'll be much easier to solve. So yeah, this is a very simple example of steganography. So I'm going to stop sharing this. So I'm going to give you all a second if you want to look at this file later. Go ahead and save and download this file. And I'm going to start sharing my screen again. So take a moment to download the file if you want. And now I'm going to start sharing my screen again. Okay, so we're back to the presentation. Okay, so that's what steganography is. And that example kind of should have explained a little bit. So I'm sending that picture, but I'm trying to hide the fact that there was a secret message in it, right? So that's basically what steganography is. It's when you're concealing data within other data. And in this case, I was concealing text within a picture. So let's talk about some of the steganography techniques. And one of the most popular ones is the least significant bit. It's embedding messages within the lowest bits of images. And that's why when we were talking about binary, I highlighted that the rightmost bit is the least significant bit because the value of it is so low. It's 2 to the power of 0, right? And then the most significant bit is all the way to the left. So changing the most significant bit would change the number by a lot, right? But if you were to change, let's say, the least significant bit, it wouldn't really change the number by a lot. So what happens in image files is that you could change the value in images in the pixels by altering the least significant bit. it's not going to have a significant impact on the images, and obviously they will not be detectable by the human eye. The change will be so minor that you will not be able to see. To uncover those images, you would have to use a steganography decoder to hide information. Other ways of hiding information was a way that I showed you, where you take some text and you put it in that file. You can hide information in the metadata. You could encrypt a message and put it into the metadata, and then someone would have to decrypt it, extract it if they know your key. You can use file headers to hide messages. You can encrypt using, steg files. You can use programs. There's a lot of programs like StegHide, OpenStego, Snow, which is a really cool program. What Snow does is it makes use of all the blank spaces in documents. So if you have a document, you realize there's a lot of white spaces between commas, periods, and it uses those spaces to hide bits of information. So there's multiple different ways. People are getting creative, and it's really hard when you look at a file to really, if I gave you an image file, it would be really hard for you to see if there's steganography within it, and then what type of steganography is within it. So it can definitely be challenging. There's also audio steganography, and you can embed secret messages into digital audio. Again, they use least significant bit, and another method called echo hiding, which has to do with the wave lengths. So let's do a simple, I promise this challenge is pretty simple. So it is called What Lies Within. There's something in the building. Can you retrieve the flag? It says there is data encoded somewhere. There might be an online decoder. That's my hint. So let's see what, so here's a building image. If I zoom into it, I don't see any particular message hiding, but it tells me to use an online decoder. So let's try to use an online decoder. Online steganography decoder. Okay, see if this will work. So let's go into decode and downloads, and let's decode this buildings. Let's decode it, and there we have our flag right over here. So that was not such a bad challenge, right? That was pretty simple and straightforward. So that's an idea of what steganography is. And CTFs always almost have a couple to few steganography challenges in the forensics section. We are almost done, so hang in there. I know it's been a lot of content today. Okay, let's move on now to network traffic. And today we're going to touch briefly on network traffic, and then in Forensics 201, we're going to talk about more complex, how to analyze more complex network traffic. But today is going to be an introduction into network traffic and what I'm most excited about, Wireshark. So what is a network? A network is a computer network is two or more computers that are connecting with one another for the purpose of communicating data electronically. What we have going on right now from my computer to everybody else's computer that's watching this is a network connection. And that network connection, if we wanted, we could capture that and all those packets that are being sent to you guys while I communicate with you, and while your computer captures all that data that I am sending to you right now, and as it watches and what it sends back. So that is a network. So it's really important to analyze network traffic and data captured in transit between devices during forensic investigations, because a lot goes on the network, right? You want to know what websites were visited, which two computers established a connection, was there any file sharing that was done, the HTTP protocol, like who visited what website. And so you want to capture all of that network traffic because it could have a lot of important forensics information inside it. So network data can be collected from firewalls, switches, routers, network logs, etc. And two of the main tools that you can use to analyze and review that traffic is Wireshark and Tcp Dump. we're going to be discussing TCP dump. Sorry, not TCP. We're going to be discussing Wireshark only and not TCP dump. It's similar to Wireshark. You can get Wireshark across all operating systems, and it is a free open source tool, and it is a very helpful, useful tool. If you are interested in a career in cybersecurity, Wireshark is going to be one of the most commonly used tools you will be using. So it's really key that you get familiar with it and that you have a good understanding of it. And even during Ctf challenges, Wireshark comes in really handy. So before we look at network traffic, we have to understand how computers and networks communicate with one another. And that is through protocols. Protocols allow computers to speak to one another. They define a set of rules that allow computers to talk with one another. And the two key protocols, which are at the transport layer, which control the transportation of data, are the UDP protocol and the TCP protocol. UDP protocol is also known as the user datagram protocol. The UDP protocol is a connection-less protocol. When you send data to, let's say I want to send you some information, my computer is just going to fire it off to you. There's no confirmation that your computer received it or it didn't. I will just send it to you. I will just throw it there, and it's not my problem if it gets there or not. That's kind of what the UDP protocol is like. And common applications are video chatting, online gaming, and it's a fast protocol. It's faster than TCP. So TCP is a transmission control protocol, and to set up a connection, a handshake is performed before. So if I want to communicate with you, my computer is going to send a SYN packet first, which means synchronize. Then your computer is going to send an acknowledgement back to my computer saying that I received your SYN packet, and here is my SYN packet because I also want to establish that connection, so synchronize. And then after I receive their synchronize, I will acknowledge that, and then our connection is established and we can start communicating with one another. And the same is done when you're tearing down. So when the connection is being closed, I'm saying that that's all I wanted to send for today. I'm going to now close our connection. I'm going to send a FIN packet. Your computer is going to send me back an acknowledgement packet as well as a FIN packet, and then I'm going to send an acknowledgement packet acknowledging your FIN packet, and the connection is closed. So those are the two networking protocols, TCP, UDP. And I mentioned this because when you are going to be using Wireshark, you're going to notice a lot of TCP, a lot of UDP traffic. You will notice other traffic as well, but we've talked about the HTTP protocol and web security, so you understand what that is for. There are other protocols, but most of the time the Ctf challenges focus within the HTTP, UDP, TCP protocols. So let's talk about Wireshark. Wireshark is a protocol analyzer, network packet analyzer that allows you to see recorded network traffic. So if I were to record traffic between my computer and your computer and capture it, Wireshark would allow me to actually view that traffic. And this recorded traffic is stored in a PCAP file. And why I highlighted PCAP is because a lot of the times you're not going to be given a hint or anything. You're just going to be given a PCAP file. You're going to be like, what is this? And the first step would be to open up that PCAP file in Wireshark. So what are packets? Packets are a unit of data transmitted over the network, and the packets contain data and other important information such as destination IP address. So when I'm communicating with your computer and a packet is being sent, we're communicating over UDP because we're video conferencing, so it's going to say UDP packet, source is Samin's IP address, and destination is your IP address. And we're communicating at a specified port number. So that is what Wireshark will allow us to see. Here is a screenshot of what Wireshark looks like. So let's take a look here, what's going on. So these are the packets, they're numbered. Here's the timing. Here is the source IP. The source is who is sending the data, and this is the destination IP, who is receiving the data. And as you can see, we see some protocols. We see the TCP protocol, and we see the SYN. We see the ACK packet, so it's being acknowledged. we see an HTTP protocol right here, and you guys remember GET. We talked about how this means that this person is maybe trying to watch a Netflix show or something. This is again a TCP, an ACK packet, another ACK packet, a TCP SYN packet. This is a TCP SYN ACK packet. So we could see that this computer initiated a connection using the SYN packet, and then this computer acknowledged the connection and sent them back a synchronization packet, and then this computer again acknowledged their SYN packet, and the connection was started. So, and then below here, you can look at the actual details of exactly, you can see within each header what's actually going on, and here is going to be the hexadecimal ASCII values of what's happening. Now, it's really important that I'm going to give you a tip. So you can follow a protocol stream to see all the data that is generated through that particular network connection. And following a stream will give you a complete picture of all of those packets that fall within that particular connection. So instead of manually looking at it packet by packet, you could just look at a stream to see all of the packets that were sent in that one particular connection. Packets do have a limit of how much data can be sent, so data is often broken up and sent in multiple different packets. So viewing that packet by packet would be very time consuming, so it's much easier to view a stream. Oops, okay. So now let's actually look at a Wireshark packet. And let's solve a problem from the Ctf. So we're going to be solving the Shark on Wire 1 problem. So here is the packet capture, and I'm going to open it with Wireshark. It's asking me for a password. Okay, here we go. So here is the packet that we were given. And it includes a lot of, protocols we might not have heard of, but that's okay. We don't have to worry about that. And these colors, they all mean something different, and you can, in your setting, go and change the color for something. So I feel like the red color is for TCP connections or specific TCP connections, reset connections only. So this is a packet capture we're given. Does anyone know what can I do? Like, this is a lot of data. This is a huge amount of data. What should I do? What should my next steps be if I was given this packet capture? How would you approach this problem? A lot of people are saying let's filter for the word Pico, but it unfortunately doesn't work like that within Wireshark. We can create a filter, but we can't filter like that. So let's filter for, let's look at TCP connections. Let's filter for TCP connection. So to filter for TCP connection, I would do TCP stream and apply the filter. And here are all the TCP connections. And I can see these are not normal TCP connections. And why aren't they normal TCP connections? What gives away the fact that these TCP connections are not normal TCP connections? Does anybody know? Does anybody know why these TCP connections, first of all, they all have that red error thing on them. Not error, but like red kind of warning color to them. And they don't look like normal connections to me, normal TCP connections. Yeah. So it has to do with the fact that there are, this is not a normal connection because it's reset packets. A normal connection looks like SYN, SYN-ACK, and ACK. So that is not happening here. This is not a normal connection. These are reset connections and a lot of malicious attacks often take place by sending your computer reset connections, and that is outside of the scope of this workshop, but this does not look like a SYN-ACK type connection. It doesn't look like a successful handshake. So I doubt that there is any data in here because it's a reset connection. But anyways, let's follow this TCP stream. And as somebody mentioned that there is no content in here as well. It's blank because there is nothing. They're just reset packets. So now we looked at TCP. How about let's look at UDP and see if we can find anything interesting in UDP. Why is it not allowing me to filter? Okay, well let's view the UDP packets. As we can see, a lot of these, okay, so this says malformed packets, so it doesn't look like there might be anything here. Let's look at this packet. This packet is from source 10.0.0.2 to destination 10.0.0.13. Okay. And this one is from the same address, but the last is to .12. It's a different machine. Let's see anything. I don't know. Maybe let's okay, so I see a P in this one. I don't know if that means anything. This IP address, right, I see Pico right here, right over here. So let's follow this stream. Follow UDP stream and see what happens. Okay, they're trying to trick us. It just says, so that connection established was Pico, 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 Pico. That's all of their packets that were sent. Okay, so and that was from the source 10.0.0.6 to 10.0.0.11 IP address. So now we know not to look for that one. Okay, so that one, the 6 to 11, is not legitimate because it has a fake. Okay, this one has a P, so let's see what all of the packets look like together. Let's follow the UDP stream. Oh, there we go. There is our flag right here. So as you saw, that was not easy. It was not easy to find what we were looking for right away, but we had to analyze something, but analyze each of the packets. But what really helped us was knowing what normal TCP packets look like, because then we could eliminate TCP packets as an option, and we could focus on UDP, because the TCP packets were not a normal connection. They were reset flags. They didn't have the SYN, ACK, and ACK. So I just got a couple messages to go over this one more time. So let's go over it one more time. Someone is asking where I saw the letter P. So as I was going through these packets, I came across P right over here in the data. But this is the data within the packet. As you can see, here's the data, and this is the data within the packet, and I saw a P. And I'd already tried some of the other, and it looked like, so if you look here, it said P, and then here was an I right here, and then this is the same connection. And then there was a C in this packet, and then there was an O, Pico, and then capital C, capital T, capital F, and that made me want to follow this stream. And then, so what I did was I followed this UDP stream, and all the packets combined, that was the flag it gave us. So it can be tricky and it can be time consuming, but it's important to use the networking knowledge we have, and that knowledge of what the normal connections look like, and to see how, and also what really helps is following the specific streams. Yeah, Abira is right. So each packet was carrying one character, and when we followed the stream, we were able to see the entire stream put together. So when you follow a stream, you could see all of the packets that took place in that connection, and that will give you an overall picture. They will not expect you to, put together the packets one by one, because that will be very, very hard. So it's really important that you follow the stream to see all of the connections together. And again, we're back. Let's go back. Let's clear all the filters. We had this. The reason we didn't focus on TCP was because all of these were reset ACKs. They were not normal TCP connections, which is SYN, ACK, and ACK. I didn't see any of that. I saw SYN, reset ACK, and then this SYN ECN, which honestly I have no idea what that is. And this is the ARP protocol. ARP protocol is when you want to figure out which computer to send a message to. So it's just mapping out what MAC address belongs to a specific IP address. so that we know that there's not going to be any sort of data in there. So TCP, UDP are the transport protocols that carry some data within them. And it could also have been HTTP, but I saw there wasn't too many HTTP packets. There was mostly UDP and TCP packets. And most of the time you could ignore these other protocols unless they tell you specifically that there is a flag in that specific protocol. So that's how we would go about solving a Wireshark problem. There are other problems with Wireshark on the Pico CTF, so I encourage everybody to try. They're very similar. You have a packet capture, and then you have to try to find the stream that you can extract the flag from. In 201, we're going to look at encrypted packets and how we can, decrypt those packets, or encoded packets, or, reverse engineering the packets that are malinformed. So that was, the 201 courses are going to be in 2021, starting in January 2021. So that was a little bit about Wireshark and how you would exactly solve a problem. Just keep in mind that when you have a PCAP file, you have to open that file with Wireshark, and then you'll know. And if it's anything to do with network traffic, it's also going to be a Wireshark problem. Let's look at, let's summarize everything we learned today, and we learned a lot of stuff today. So we learned about the importance of collecting evidence after an incident to make sure that volatile evidence is not lost and it's captured first. And again, volatile is your CPU cache, your RAM, and least volatile is your hard drive. We talked about numbering systems like binary, hex, and ASCII. Binary is base 2, hex is base 16, and ASCII is an encoding scheme for all of your characters. We talked about how file headers include important information about the format of the file. So if there's no extension, that's nothing to worry about, because a file header can tell us what type of file a particular file is. We talked about hex editors, which allow us to view and edit binary files. As mentioned, I highly recommend that when you're actually playing the challenge and just to practice, you download a hex editor, because the ones online, they're great. They allow you to view, but they will not allow you to make significant changes as easily as having one on your local drive, your actual computer will. And I linked some free ones, and I will share them again. So make sure that you download a hex editor when working with hex files, binary files. Steganography allows us to hide the fact that we are sending a message. And most of the times it's going to be within images, but then there's also audio steganography, and it uses a concept a lot of times, what's known as least significant bit. By modifying the least significant bit, you can make small changes without them being noticeable to the human eye. And then we talked about Wireshark, which allows us to capture and analyze network traffic. When you're given a PCAP file or network traffic, you have to use Wireshark to analyze that traffic. So that is a summary of everything we learned today. And here are some resources. Why don't I copy and paste all of these resources in the chat? You guys all have them. And if you don't have Wireshark, you can download Wireshark at wireshark.org. And something else that is important are the hex editors. So let me just get you a link for all of them. If you're going to be using a Linux distribution, Bless is the best one. At least for me, there's lots of free ones for all different operating systems, but here are some of the ones that I've used before. And that is it for today. Thank you everyone for your time. We're going to be here for any questions that you might have. And a reminder to register for next Wednesday's workshop, which is about women in cyber. Registration is required. Without registering, you will not be able to attend. And if you have any concerns about that, please let your teachers know. They could email us. And if your teachers are comfortable sharing their email or something to let you attend, that can be done. And if you're not comfortable, then a recording will be sent out after the workshop. And the link to register is right over here. if you go down, and there's going to be a register here, link right there. But this is a really cool blog post highlighting women in cyber, and I recommend that everybody takes a look and reads it. So as a teacher, you could share that link with your students, and they have to register themselves. Every student has to be registered for that workshop. What will be included in that workshop? That workshop is going to be all about women in cyber, and it's going to be a panel, and you're going to get to hear from women who work in the cybersecurity industry in different companies, and they're going to be doing a little Q&A. They're going to be sharing their experiences in an all-women panel, so all the speakers are women. And then the week after, we'll continue with our regular workshops. The week after, the 18th, will be our reverse engineering workshop. Yes, so registering for that one is independent. It's not related to these workshops. These workshops, the process will be the same. You can share the link with your students, but for that particular workshop next week, you have to have the students register. And yeah, the workshop is over now. And please, if you don't have any questions, feel free to step out and leave whenever if you don't have any questions. And so next week, we're not going to be having a workshop. There's going to be a panel on women in cyber, and we're going to continue the week after with reverse engineering. Yes, all students are welcome to join next week's workshop, even if they haven't attended the previous ones. They just have to make sure that they register and they can attend, of course. Thank you. Have a great night, everyone.